is my Physics 2211 Lab 5, the falling Slinky. So the purpose of the lab was to measure and predict the motion of the Slinky as it dropped from rest. I compared the observational model found during tracker and the computational model found in GlowScript to see the effect of the forces on the Slinky's position and determine if the Slinky stays motionless, if the bottom of the Slinky stays motionless. I analyzed the information on tracker and GlowScript to develop these models. So a preview of the results is that the motion of the Slinky in the observed and computational models are constant due to equilibrium forces acting on the system. So some fundamental principles are Newton's second law, like the velocity update formula and the position update formula. And then there's also the force of gravity, which is gravity in the y direction. And then drag force, and that's negative bv squared. And then there's also the force of tension, which is opposite to the force of gravity. So because force of gravity is moving downwards, the force of tension is going to be moving upwards. So here is the tracker video, and you can see that the Slinky is falling down. And then for GlowScript, we're going to separate into two codes. So the first one is going to be the time as it reaches all the way to this position. And then the second part of the code will be when it goes to this position as it falls down. So the mass, here's the mass. We have the initial position. We have the initial velocity. The system is going to be the spring, and the surrounding is going to be the earth and the human hand. So here's the GlowScript code. So here we have the mass of the Slinky, we have the position and the velocity of it, we have the time, delta t, gravitational constant, we have j hat, which is going to be 1 in the y direction. We have our proportionality constant, and we made that 1.88. So for the first time, as I said before, we're going to have the force of gravity, which is negative mg, and then j hat because of the y direction. And then we have force of tension, which is going to be also mg j hat. So it's just going to be the opposite of the force of gravity. So that's your net force. And then you have Newton's second law right here. You have the velocity update and the position update. And then for the second part of the code here, you have the second while loop. We have the force of gravity, we have drag force, and then F net is going to be the force of gravity and drag force. And then here we have the velocity update and the position update formula. So here you can see the two models. So the blue line is actually the observational model, and then the red line is going to be the computational model. And as you can see, they're actually pretty close to each other. So some possible sources of error for why they're not exactly the same is that some forces may not have been accounted for in the computational model, like the air resistance and that such. And then there may have been some error when tracking the center of mass of the Slinky. So, because I was really struggling with tracking that center of mass, so that could be a reason. And then some ways to improve the graph could be separately tracking the top and bottom of the Slinky. I did track the bottom of the Slinky, and more accurate data about the motion of the Slinky. So what does it mean? So does the bottom of your model Slinky stay stationary just like in the video? The bottom of the Slinky does remain stationary because the force of gravity in the negative y direction is equal to the force of tension in the positive y direction. The bottom of the Slinky is at static equilibrium, and it has a net force of 0, and the bottom stays motionless until the entire Slinky reaches the ground. And that can all be seen in the tracker video I showed earlier. So conclusion, I developed an observational model through tracker and a computational model through GlowScript to compare the position of the bottom of the spring of the Slinky as it falls to the ground. The observed and computational model are similar to one another. However, there were some differences, and they were probably due to the lack of certain forces in the computational model or some human error made during tracker. And the bottom of the Slinky does remain stationary until the Slinky is fully compressed. But if we did track the top of the Slinky, it would be very different. So it would be really interesting to actually add that to our model.